Hello and welcome back to Organic Chemistry Companion. In this video, we'll be going over electron configuration. So what is electron configuration? Well, this is really just a way for us to represent the electrons that are in an atom. And this is important because it helps us understand how the atoms bond and interact with each other to form molecules. And so if you've ever seen the cartoon description of an atom like I've shown on the left-hand side here, this is partially correct, and it kind of helps us think about how the atoms are organized. So you have the protons and neutrons in the nucleus there in the middle, and then you have electrons orbiting the nucleus on these orbits that I've drawn here in gray. And I mentioned this is kind of correct, but typically as organic chemists, we prefer to think about where the electrons are located and how they behave in terms of orbitals. So what is an orbital? Well, an orbital is an area of space around the nucleus of an atom where an electron can exist. And electrons are moving really, really fast and they're very small, so it's actually almost impossible for us to say exactly where they are at any one point in time. So an orbital is really just a mathematical tool that allows us to think about where an electron could reside outside of a nucleus. And so there are different types of orbitals. They all have different energy levels, and the different shapes of orbitals are represented by different letters here. So you have s orbitals, which are basically just shaped as spheres with the nucleus being in the middle there. P orbitals, which look like dumbbells. So there are 3 different p orbitals, and they're aligned x, y, and z, depending on which direction they're protruding from the nucleus. And then you have d orbitals. They have kind of funny shapes like this. The nucleus is in the middle there. This is just one of 5 different d orbitals. And you typically will encounter d orbitals when you're working with transition metals and elements with higher atomic numbers. Okay, and when we think about how to put electrons into the orbitals, we first have to consider in which order we have to fill them. And so there's a little trick you can use if you write out all of the orbitals like this. So the energy level is 1 through 6 as we go down, and then at each level you're going to add a letter here. So the 1 energy level only has a 1s orbital. In the 2 energy level, there are s's and p's, 2s, 2p's. In the 3rd energy level, you have s, p, and d. In the 4th energy level, you have s, p, d, and f. And then beyond that, we don't add any more letters. So there are only s, p, d, and f orbitals. So you have 5 s, p, d, and f, and then 6 s, p, d, and f. So to determine in which order we fill these orbitals with electrons, you're actually going to draw a diagonal line through these like this. So first we're going to fill the 1s orbital with electrons, and then beyond that, we're going to fill 2s, and you're going to draw this diagonal line in between the 1s and 2p like this, going through 2s. So that tells you that 2s is the next energy level that you're going to be filling. The next line you draw through 2p, 3s, so the electrons you would add then go into 2p and then the 3s orbital. Then you draw in between 2p and 3d like this. So the next electrons go into 3p and then 4s. And then draw this line again, going through 3d, 4p, and 5s, and so on. Okay, and when we're adding electrons into this diagram, there are a few rules that we have to follow. So the first rule is called the Aufbau principle, and that just states that we have to fill the lowest energy orbital first. And so that's pretty straightforward. We just go to the bottom of the diagram. The 1s orbital is the lowest in energy, and so we're basically just going to add an electron into that, like that. And we represent electrons by these one-headed arrows, and so this one is pointing up, and that leads me to the second principle that we have to follow, and that is the Pauli exclusion principle, which states that electrons have spin either up or down, and the paired electrons within an orbital have to have the opposite sign. So if we put the first electron into this orbital with an up arrow, the second electron that we put in has to have a down arrow. That's just a convention. So finally, the last rule that we have to follow is called Hund's rule, and that states that we have to fill each orbital with 1 electron before we start pairing them up. And so that'll come into play in the 2p energy level up here. So what we're going to do as we go up in atomic number, we're going to be adding electrons next in the 2s, remember going from bottom to top. And then once we get to 2p, we have to add 1 electron into each orbital before we start pairing them up like this. So pretty straightforward, just a couple of rules to keep in mind as we're adding electrons into the diagram. Okay, so let's do a quick example. So we're going to draw the electron configuration diagram for helium. Now, to determine how many electrons we have to place into the diagram, we have to look at the periodic table first. Okay, so here's our periodic table, and helium is up here. If you take a look at the atomic number, which is in the upper left-hand corner of the atom symbol there, that tells us that helium has 2 electrons. So that means there are 2 electrons we need to add into the electron configuration diagram. Okay, so back to our diagram, we just have to add 2 electrons here. We start with 1s, again, lowest energy level first, up spin arrow, down spin arrow. So 2 electrons, and that's it. Now, if we wanted to write the electron configuration in number and letter form here, what we would do is just write out the energy level, the orbital 1s, and there are 2 electrons in the 1s level, and that's it. So that's how you would write it. Pretty easy. Okay, now let's do oxygen. So look at the periodic table again. So oxygen is right here. It has an atomic number of 8. So that means there are 8 electrons that we need to add into the electron configuration diagram. Okay, so let's go ahead and add those electrons. We need 8 total. So 1, 2, then we move up to 2s, 3, 4, 5, 6, 7, 8. So that's it. That's our electron configuration diagram for oxygen. Now to write this out, what we would do is just write the orbitals that have electrons in them. So 1s has 2, 2s has 2, and then 2p has 4 total electrons. That's the other way to write this. Now there's a shortcut that we can use to abbreviate this, and this is going to come in handy, especially when you're dealing with atoms that have much higher atomic number. So you don't have to write out every single orbital and number of electrons in each orbital. And that is to use noble gas notation. So to do that, we're going to look at the periodic table again. So oxygen is right here. And what we want to do is look for the noble gas that is just below oxygen. So if we go all the way back, helium is actually the noble gas that is just below it. So noble gases, again, are all in column number 8, this last column of the periodic table. So helium is right there. And what we can do is, let's go back to writing our formula. We can actually abbreviate helium and its electrons just by doing this, writing it in brackets. And then all we need to do is add in the electrons that are above the elements above helium. So 2s2, 2p4. And that's it. That's a lot easier than just writing out all of the electrons. Okay, so let's do a slightly more complicated example. Let's do zinc. So zinc, if you look at the periodic table, has 30 electrons, and we need to add those into the diagram. So let's start with 1s, then go to 2s, 2p, remember add them one at a time, and then go back to the beginning, 3s, 3p, 4s, and then 3d. So we fill each of these with 1 electron, and then go back and pair them up. So with 30 electrons, zinc completely fills the 3d orbitals with electrons there, and this is the electron configuration for zinc. Now, to write out the electron configuration, what we could do is write 1s2, 2s2, 2p6, etc., or we can use our shortcut and use the noble gas shorthand for that. So let's go ahead and do that. So argon is the noble gas that has the atomic number just below zinc. And then to add in the additional electrons, we write 4s2, 3d10, and that's it. Now, how would we do this if we were asked to write the electron configuration diagram for zinc with a 2+ charge? So the simplest way to do this is to just draw out the electron configuration diagram for the neutral atom and then remove electrons. Now, there's a subtle rule we have to follow here when we're taking electrons out, and there are d orbitals in play. So we actually are going to take electrons out of the 4s orbital before we take them out of the d's. And so to do that, in this case, we need to take out 2 electrons to account for the 2+ charge. So we're going to take out these 2 electrons in the 4s orbital before touching the electrons in 3d. And so to write the electron configuration, we would simply just take away that 4s, and we have argon 3d10. Okay, so now let's talk about how we would handle this if we have a minus charge. So zinc with a 1- charge there. Now, we don't typically see transition metals with negative charges like this, but just for the sake of explaining how to do this, let's pretend that we do have a zinc 1- that we have to draw here. So the way you're going to do that is actually very similar to the way that we did the positive charge. So you draw out the electron configuration diagram for the neutral atom, and then in this case, we need to just add 1 electron to account for that negative charge. So we would add the 1 electron in at the 4p energy level, and then to write the electron configuration, we can stick with the argon core there, 4s2, 3d10, 4p1. So that's zinc with a 1- charge. So if you found this video helpful, please give it a like. That really helps my channel reach as many people as possible. Subscribe if you'd like to see some more helpful chemistry tutorials, and comment below if there are concepts or practice problems that you'd like to see me cover. I do offer one-on-one and group tutoring, so send me an email at organicchemistrycompanion@gmail.com if you'd like to get in touch. Thanks for watching.